So welcome back to ENAE 788M, Hands-on Autonomous Area Robotics. So in last lecture we talked about structure of motion and we saw how we can reconstruct scenes using multiple views. So let's now talk about more fundamental things like optical flow. So let's move on to the topic. So let's talk about if you have an image like this and if the objects are moving, right? Let's say the objects are moving something like that. So they move from their original position to their new position. So what's going to happen is like these are the vectors, right? This particular point moved from here to here, this particular point moved from here to here, and you can see all the vectors, right? So this is from the moving objects. What if the camera is moving? Let's say I'm going towards this object or I'm going inwards, right? You will get something like this. The object might become bigger and they might go in some random directions, right? Depending on in which direction I'm moving. So you will see another set of vectors, right? So what can these vectors tell us? Like you saw these are the vectors from the first case and these are the vectors from the second case. Can we basically detect anything from these vectors? Like how things are moving or how the camera is moving? Can you tell us about that? So this is basically the fundamental idea of optical flow. So let's talk about optical flow, right? Coming back to the point. So this is the diagram which I used in projection equation in the camera model lecture. So capital X, Y, Z are the 3D world coordinates, and small x and small y represent the image plane axis. Okay, so I can say that my small x equals capital X by Z and small y equals capital Y by Z. And if I want to write this in vector notation, I can say my P equals 1 by Z times capital P, right? P being basically the 3D world coordinates and small p being everything on the image plane. Okay, let's say this particular point moves from here to here by P. So if I differentiate this thing with respect to time, I'll call this P dot basically, which is the displacement, right? My P dot equals capital P dot by Z minus Z dot by Z times P, right? Now I can just rewrite this equation and I'll be like capital P dot minus equals minus omega cross P minus V, where omega is my rotational velocity, which basically is omega X, omega Y, omega Z, right? Cross P, which is basically the position of the 3D world coordinates of the same point P, minus the real 3D world velocity Vx, Vy, Vz. So everything here is in the vector form. So in optical flow, there is an important assumption that my pixel intensities do not rapidly change between the consecutive frames. So that means in, let's say, my first frame, let's say for some particular pixel, I have intensity value, let's say 235. In the next frame, I'm not turning off the light, for example. That value should remain somewhere near 235. Should be somewhere around, let's say, 225 to 240, somewhere in that range. If it goes like 100 or 50, that assumption fails and your optical flow will not work basically. So very important assumption. So that's why if you let's say if you're flying your Bebop Husky using its onboard optical flow sensor, if you turn on off light like after each second, that optical flow will that estimation of the motion will start giving very bad estimates. So that's why this assumption is very important. Okay, so moving on, this equation we read, right? Now I can write this in more vector form. I can say that my P dot equals 1 by Z E3, where my E3 is in a unit vector in my camera Z direction. So E3 cross P cross V plus E3 cross P cross omega. So there's a derivation for this. If you want to go look it on the internet, how to derive this equation. Okay, this basically comes directly from the above equation. So if I have this, if I want to expand this, I can write this as P dot equals 1 by Z x Vz minus Vx, y Vz minus Vy, and this matrix into omega. Note that this particular part is only responsible for translation, and this particular part is only responsible for the rotation. So this is called the translation flow, this is called the rotational flow. And one more important thing is my rotational flow is independent of the depth, but the translation flow has this entity 1 by z. So let's talk about pure rotational case. So for the sake of simplicity, let's assume that every scene that I'm looking at is rigid. Okay, so if the flow field is purely rotational, we have no depth information, right? So my p translation is 0. So I can say that my rotational flow is this matrix times the omega, right? But if I want to plot this, how my flow field will look like, let's say this is my camera z-axis and this is all the features I'm seeing. So camera is looking at this direction, right? And if I rotate this camera by z-axis, something like this, my flow field by pure rotation about z-axis would look something like this. Okay. Now if I have pure translation, let's say this is my z-axis, and if I'm moving this camera towards the scene, right? So I can write my translation something like this, right? From the previous equation, obviously. So if you move your camera in this direction, you will get something like this, right? So you see every pixel is moving, like if you're moving inwards, every feature is moving radially outwards to the direction, right? So one very important thing to note is that if I join this line and this line, these lines are basically, they have a lot of collinear points if I'm going directly inside. So if I join these lines, something like this, so I will find a common point which is known as focus of expansion, or basically this is the same thing as the epipole for a moving camera. So when we studied epipole, we studied in two different views, right? This is exactly the same thing. Like these are the two different views. Your camera is moving, so this is like from the previous view and the next view. So that's why it's called focus expansion or the epipole. Now if you are moving inwards, for example, if you're moving inwards towards, let's say, like this direction, like a little right direction and inwards, you will find the flow something like this. If you're moving from let's say left to right, your flow fields would look like something parallel from right to left, or the inverse basically, right? Now if I'm rotating about x-axis, so you have to visualize these flow fields. Like you just don't believe this will actually work. So try to move your head, for example, in the previous case that we saw, this particular case, try to move your head from one direction to other direction and see how the features in your image plane are actually changing. Okay, now try to rotate by something like this, see what's happening. Like just try, if your camera is pointing towards this direction, just try to rotate your like forehead and see how the features are moving, right? So you will get something like this, like more parallel lines in between and more curvature on the corner of the image. So there's one more ambiguity I want to talk about here. So if you have a very narrow field of view, right, you will see something like this. Let's say your field of view is 60 degree or 50 degree, right, and you are rotating about x or y axis with respect to your camera, right? So the only flow fields you are gonna see is in this region, right, which if you see is similar or exactly the same as your pure translation flow, as if you were moving from your from left to right direction, right? But if you want to use this flow to basically find your change in rotation and translation, that's a problem, because if you don't have a very wide field of view camera, you would never know just by seeing the optical flow that is this flow due to my translation or rotation. That's why when you are doing odometry, like visual odometry, you require a very wide field of view camera. That's why every living bird or insect that navigates around, they have a panoramic vision. They have field of view like 150, 170, or even more than 200 at times. So that's why you need, if you are on a drone and if you want to navigate, you want to have a very wide field of view camera to basically to remove these ambiguity. Okay. So that's why what one more important thing I want to add is when people use visual inertial odometry, so they get pose estimates from inertial measurement units or IMU sensors and the camera. So cameras are actually generally very good when they are estimating the translation part of the pose, right? And IMU are generally very good for the rotational part. IMU is not very good if you want to measure how much I moved. They're very good at orientation, they're not good at position. Camera is vice versa. Camera is very good at position, but they are bad at orientation in general. So what people do is they fuse the rotation from IMU to the position of the camera. So this is how a generic VIO works basically. This is one important idea, and you want to use your cameras. You want to use a very wide field of view camera to get a very correct estimation. Okay, so this is how people actually represent optical flow. So the green lines on the left you're seeing is just the vectors which are being drawn, and on the, so this one is like the sparse optical flow because you're detecting features, right? And this is more dense optical flow. This rather than feature is based on the nearby blocks and everything rather than just one particular point. So the color you are seeing basically represents the direction. So remember your hue saturation value HSV scale, that circle basically that changes from yellow to green to blue basically, right? So this is based on that hue scale. So depending on the direction in which the flow directs, right, the color changes, and the intensity is depending on how much the magnitude of the flow is basically. So one more thing, do you guys know about MPEG compression and things like that? How do they make a, let's say 3 GB movie to a 700 or even a 300 movie? So basic concept they use is optical flow, for example. So the assumption is everything is a continuous stream, right? It's not changing much. So rather than saving frame by frame, if I just compute optical flow, let's say I have first frame, right? And I'm storing, let's say 256 bit information in that one frame. But I know that next frame is almost continuous and I just need to add just 8 bit of information to get the next frame. So rather than actually saving the next frame, I will save the optical flow between the first frame and the second frame. So this is the basis of the MPEG compression, which is very common today. So let's move back to what focus of expansion we read in the previous slides, right? So focus of expansion is basically my Vx by Vz in X and Vy by Vz. So you have focus of expansion is a point on image plane which has both x, y coordinates. So for Vz equals 0, focus of expansion can be basically at infinity if you put Vz equal to 0 in this equation, right? So you remember this flow translation value from the optical flow equation. So you can use that equation to find time to contact or time to collision. So this is a very useful thing that you might use in your next projects. So I can just rewrite the equation. I can say that my time to contact is z by vz, right? My depth by the velocity I'm moving in the depth direction basically, or the z direction. So using that, I can say my vz by z equals my norm of translation flow divided by my norm of flow minus my focus of expansion. So this is a very important thing to learn. So the points at the same radial distance from FOE have the flow vectors length proportional to the inverse of the depth or inverse time to the collision basically. So this is an important thing which actually have been used by nature as well. So I'll give you a very good example here. So have you ever heard about the torpedo gannets? So these are the birds who basically dive in water to basically catch fish. So let's see a video. Like there are a bunch of gannets who are basically trying to dive into deep sea to catch fish, right? So you can see the way they are doing it. They have a monocular vision basically. They have two eyes, but they don't have a stereo vision per se because they don't have a very common field of view. And they are moving at 60 miles per hour. That's insane, right? Even a bad move, if let's say they couldn't, you're seeing that they're curling their wings inside just literally milliseconds before they hit the ocean, right? So this is being computed in their brain or whatever using the concept called time to contact from optical flow. So this is a very cool thing. Like if they miss by few milliseconds, they're gonna break their neck. They're moving at 60 miles per hour. So this is a very cool concept to learn. So it's been nature all around. So yeah, this bird basically saved this fish from drowning. Nature is amazing, isn't it? So yeah, that's it for optical flow. So I would suggest you guys to use optical flow. Not sure if you want to use that for the next project, but it's a very good way to estimate your position or how you are moving. If you have a down facing optical flow sensor, or if you have a down facing camera, you can basically write your own optical flow algorithms and things like that. So yeah, just go through this, read more about optical flow online, and read about it. And we'll talk about more regarding this, that can we use something from down facing depth information to have a better estimate of your position and velocity. Okay, so that's it for now. See you in the next class.